Hey everyone, I want to welcome you to this workshop that's at the Keck Institute for Space Studies, and I'm very excited to start it off this morning. I'm Mike Brown. I'm a professor here at Caltech, an astronomer, and our very first talk is Karen Meech, who's an astronomer at the University of Hawaii. She studies comets, icy bodies, volatiles in the outer solar system, and how they help to form our own solar system. And she's going to be telling us about some of the very exciting science from interstellar objects, long period comets, near Earth objects. Karen.
Well, thank you very much. It's quite a challenge to do all of ISO, LPC, and NEO science, and I've been told I only have 3 hours to do it. So my specialty is more on the LPCs and ISOs, so you'll notice that the talk is a little bit heavier in those areas. So let me get started with a little bit of motivation why we care about these things. I'm coming at it from the astrobiology perspective. Life requires water. And so one of the big motivations in planetary science is to understand how you form habitable worlds. And in fact, as of today, there's over 14,000 exoplanet or exoplanet candidates. And what we would really like to do is understand how you form a habitable world from both the physics and chemical processes. Right now, we're starting to get beautiful images of protoplanetary disks, but this doesn't get into the region where the habitable planets are. By the 2030s, we might have the technology that we can really start to watch this process happening. But as of right now, we have only one solar system where we know there's life, and that's ours. And so the best place to start on how you form a habitable world is to look at the processes in our solar system. And so the way in which we do that is we go backwards in time by looking at the leftover remnants of the planetary building process, namely small bodies that have not been thermally altered and have been stored in cold storage, comets, icy asteroids, and maybe some of the NEOs. So some of the primitive tracers that typically are used, meteorites, these have been extremely well studied. They show us about when and where there was alteration in the asteroid belt in the early part of the history of the solar system. We have icy asteroids and NEOs that have been largely unexplored until recently with some of the exciting mission results. We have comets that have been studied for years, mostly from the ground, but now we've been having some exciting comet missions, but we haven't explored all classes of comets. Icy satellites are sometimes listed as primitive markers. We've had missions with Cassini looking up close at satellites which could potentially be habitable, but because they're bigger, they've been thermally altered. And then, of course, a really new area is the interstellar objects, which tell us about solar systems elsewhere. Now, this is a bit of a family tree of the relationship between some of the small bodies in the solar system. And what we've looked at so far in detail, we're tracing the heritage from the protoplanetary disk to today's reservoirs of where things are stored, the Kuiper Belt, the Oort cloud. We've visited samples from the Kuiper Belt, looking at the New Horizons mission. These things eventually will migrate inwards into the inner solar system, passing through the Centaur stage and becoming Jupiter family comets. And of course, this is where most of the comet science has occurred. We have had a mission of comets that originated in the Oort cloud, becoming Halley-type comets, namely Comet Halley was visited by the Giotto spacecraft. But the other side of the family tree has largely been unexplored, and that's the focus of this workshop, getting at the things that have been stored in the Oort cloud coming in for the first time, which may be even more pristine, long-period comets, a new class of comets I'll talk about, Manxes. And then, of course, we get to the interstellar objects, which are sampling the same thing, but from other solar systems. So although I'm supposed to talk about long period comets, I want to show you very briefly what we've been getting from the short period comets from 30 to 40 years of studies. And of course, I can't be very comprehensive here. But in terms of the nuclei, we've learned that comets are small. Typically, the average median size is about 1.25 kilometers in radius. The very small ones are missing, so these must be collisional products. They've been found to be very low density. Missions have shown they have very low thermal conductivity, which likely means that they're pristine on the interior, but maybe not right at the surface. We've seen from the Stardust mission, samples that were returned to Earth, that there was a lot of movement in the protoplanetary disk because very high temperature minerals were seen in the samples collected from Stardust, things that had seen 1700 degrees Kelvin. Very little surface ice, which was a surprise at first, and all comets seem to be very low albedo, reflecting their rich organic composition. More recently, especially with the Deep Impact, the Epoxy, the Rosetta missions, CO2 plays a very important role in the cometary activity, whereas from the Halley mission, we knew that it was predominantly water ice and possibly some CO2. And one of the things that was found from the ground-based observations chemically over years of studies, and this was led by Micah Hearn with a seminal paper in 1995, and then Anita Cochran and her colleagues published more results. They were looking at the chemistry of the fragment or the daughter species. The parents' chemicals sublimate from the nucleus, are released into space, they get broken up by photodissociation. And what they found was when looking at various carbon chain compounds, C2, C3, relative to CN, most comets had about the same ratio, but there were some that were significantly depleted. And it was thought that this must be telling us something about the temperature at which the chemistry occurred. But it wasn't just the short period Jupiter family comets that were affected, even the long period comets were affected. So this was a bit surprising because it was thought that these two comets formed in different regions of the solar system, yet they're showing the same sort of depletion. Once people started to look in detail at isotopes, they were not seeing also a correlation of the isotopic signatures with where we thought things formed. Coming up to the Rosetta area, which was the most ambitious and productive comet mission to date, while it was really producing exquisite detail about how a comet works, it was showing us the same sort of thing. Comets are probably preserving the heritage from the formation, the very low temperature, early solar system insight, but comets clearly seem to have formed over a wide range of distances. We certainly got a much better detail of all the chemical species that we're seeing in the outgassing and the measurements from the Rosetta target. We saw a lot of prebiotic materials, which is, of course, interesting from the aspects of the formation of life on Earth. But there were some big questions left after Rosetta. What's primordial on the comet? What is the effect of solar insolation? Many perihelion passages of the short period comets. We still don't know how and where comets form and what role they play in bringing the ingredients for life to the inner solar system. And here's the problem. If you take a look at how a solar system is formed, and I borrowed this figure from Ilse Cleves, the top image here shows gradients in temperature in the gas in a protoplanetary disk. A star system starts to form by a molecular cloud collapsing. It collapses faster near the center, so you get heating more intensely near the center. The surface of the disk gets heated, and so you will have a hot surface of the disk, interaction with ions, magnetic field, you'll have a warm molecular layer and a very cold midplane. So this will affect the chemistry. So you expect to have chemical gradients in the disk. You will have circulation both radially and vertically. At the same time that you're forming the chemistry in the disk, you're also going to have the dust grains starting to coagulate and beginning to build up the planetesimals. Once they get big enough and you get large bodies, such as the giant planets, everything starts to move around. So you set the chemistry as a function of distance from the young protostar, and the giant planets mess things up by scrambling things up. It's believed that Jupiter family comets formed in the outer disk, and then they get scattered eventually inward where we observe them. whereas the long period comets form in the giant planet region, wherever they might be. So that could be over a wide range of distances in the disk, but they may have formed in warmer temperatures. So you would expect some difference in chemistry. So when we talk about long period comets, most of us are thinking, at least I do, historically, the long period comets are the beautiful ones that you remember for their enormous tails and the presence where a lot of the public enjoys looking at them. In fact, the really bright ones are quite rare. There's about 12 on this histogram. It shows 12 really bright comets in almost 300 years. So you get something brighter than magnitude 0 approximately every 15 years, something that the general public might go out and notice. So because of this activity, it makes it much harder to characterize the long period comets. In terms of the nuclei, very little is known of the nuclei of long period comets. There have been a couple papers that suggest they're probably not much bigger than the Jupiter family comets, but we know very little about them. In terms of the chemistry, we saw from the comparison of Jupiter family and long period comets that we know that they show the same sort of chemistry in the carbon chain compounds. Mike Muma, Mike DeSanti, and other colleagues, Neil De La Russo, have been looking at the chemistry of the parent molecules that come off. And they too find the same trend, that there's some organic rich, organic normal, and organic depleted comets, and it doesn't seem to depend on where we think they formed in the nebula. However, only the long period comets seem to be really rich in carbon monoxide. So we're starting to see a paradigm change in what we're thinking of for long period comets. And again, because this is a talk about comets, I have to put in lots of pretty pictures of comets. So again, this is what we think of, but we're now seeing comets that have very different activity levels and maybe different suggestions of their formation location within what we classically call the long period comets. So let me start with a new type of long period comet, and these are the so-called Manx comets. A few years ago, it was actually in 2013, Richard Wainscoat came into my office. He's leading the NEO survey on the Pan-STARRS telescope in Hawaii, and he said, well, we've discovered an object on a long period comet orbit, which is near perihelion, about 2 AU, and has hardly any tail. Is that of interest to you? And I just looked at him and said, oh my God, yes, because most long period comets look like this, like Comet West at this distance. This is exciting. And so in fact, we started to call these Manxes because saying long period objects on long period comet orbits with hardly any tail was too much of a mouthful. So Manx is after the nearly tailless cat. So once we found this first one, we actually managed to get a spectrum of the second one. And this is what it looks like. So this is visible wavelength. This is reflectivity. So the solar spectrum has been divided out. The colorful points are the spectrum of the Manx, and the light gray lines underneath are representative asteroid spectra of S-type asteroids, things that form rocky material that forms in the inner solar system. So this typical band here, this 1 micron absorption, cannot form in the presence of water. Yet this thing had a little bit of a tail, and it behaved as if it was a thermal process, sublimation. So what we think these things are, at least this particular one, is very likely an object that formed in the inner solar system near the water ice line in our protoplanetary disk, and then was subsequently ejected to the outer solar system by the giant planets, where it resided in the Oort cloud for over 4 billion years, and you don't have to watch whole 4 billion years of the video, but then it comes back inwards into the inner solar system. So we're finally starting to see the range and diversity of things that could have been ejected to the Oort cloud. Now, what's very interesting, and Erica Bufanda is working on this with her thesis work, is we're starting to look at a lot of these Manxes, and they seem to have a diversity of colors, whereas comets seem to have just a red reflectivity of reflecting their organic composition over a fairly narrow range. The Manxes seem to have a wide range of reflectivities, so we may be seeing the diversity of what got scattered out into the Oort cloud. So This was very interesting, so I started to aggressively go after everything that we'd call a Manx. And here's an example of something that was telling us something new about these long period comets. This was one that was discovered in 2015, C 2015 ER61. And at first, I thought, this is great. It's a Manx comet. It's out beyond 8 AU. It must be really big because it's so bright. And then the next couple of observing runs, it's turning on. This is disappointing because I wanted a Manx comet. And in fact, it became an ordinary, beautiful long period comet. What was interesting about this one is if you start to model its behavior, what's controlling the activity. So plotting is a function of position along the orbit where true anomaly 0 is perihelion. This curve here, this dotted curve, represents our estimate of the nucleus brightness based on a non-detection at large distances. This curve here is how water would behave. As water starts to sublimate at about 5 to 6 AU, it knocks dust off the surface, which increases the scattering cross-section. Well, that didn't fit. And in fact, it turns out that we had a model that fit with CO2. But CO2 should start to become active if it's near the surface, near about 17 to 20 AU. And this was a bit of a late turn on. So in fact, the CO2 must be buried, and it took a while for the thermal wave to get down. Another example, this was a project of one of my students who started to look at a comet that at first we thought was just going to be a bit boring, but we had some data and it was a good short project. And as he started to model it, again, the nucleus, the water would have come up and the orange curve continued across here and down. So something turned on late and it turned out again. This is very likely to be CO2. And in fact, there were WISE measurements of CO2 production of gas that matched the model that we were predicting. And doing some thermal calculations, it turned out that both of these outbursts, which don't seem to fit the curve, this outburst here and the big onset of CO2 shows that the ice was buried about a meter beneath the surface at its deepest. Moreover, because of the depth at which the ice was beginning to sublimate, it was knocking off big particles. We saw this with the epoxy mission to Comet Hartley 2. And these icy particles, which were large, were actually producing water also. So this one had a very large water production compared to the surface area. So let's switch gears a little bit now and move to the interstellar objects. Just to remind you, in case you've forgotten, the very first one was discovered with Pan-STARRS telescope in 2019 by Rob Warwick. Here's the Pan-STARRS telescope, and it was actually discovered at the edge of this enormous CCD array. Here's the image of discovery. The follow-up images using several other facilities showed that by the 22nd, it clearly had a hyperbolic orbit with an eccentricity much greater than 1. And just to remind you, this one came in from above the plane of the solar system. This blows up the inner portion here, and it wasn't discovered until after it had passed Earth. And in fact, this was clearly an NEO. It passed within 63 Earth-Moon radii, and we wouldn't have known it if it had been on a collision course because we can't look towards the sun for the discovery circumstances. In case you're wondering, it's just recently passed the orbit of Neptune, and it's going to be in our solar system for quite a while. So why do we care about the ISOs? Well, in fact, they're giving us a sample of the building blocks of another solar system. That's what's so exciting about them. And in fact, just the same year in which Oumuamua was discovered, Engelhardt and colleagues have produced a paper predicting what the flux of ISO should be in the inner solar system based on the fact we'd had an accumulated 19 years of surveys and nothing had been discovered yet. And in fact, with the advent of Oumuamua, these things may be fairly common in the inner solar system, and we just don't see them. So what do you want to know about these things? Well, pretty much the same thing that you want to know about long period comets. You want to know what its characteristics are, the basics about the nucleus, the size, the rotation. You really want to know the chemistry. And in particular, you'd love to know something about isotopes. And then, of course, especially for the ISOs, you want to know where they came from. So hopefully you could compare it to a young solar system. Well, unfortunately, in this case, we didn't have a lot of time. The discovery and the pre-covery observation here, this is when we realized it was interstellar. You start to get observing proposals in, and you can see this is the predicted brightness just based on the inverse square law. It's fading really fast. So there was effectively 1 week in which you could do detailed observations easily. So that means after the discovery, realizing what it is, all of the observations by all of the teams occurred within about this 6-day window. And then we sent out the paper for review. So what do we learn from Oumuamua? It's small, about 100-meter radius. It's red, looks just like other comets. The boundary between these dashed lines is the envelope of the colors of comet nuclei, so it looks like comets. It had a nice rotation period that was measured by a number of teams. Here's actually a small video showing Oumuamua in the center, and if you watch it as I talk through this slide, you'll see it's getting brighter and fainter. It turns out that the brightness range from the rotation is about a factor of 10 to 1. And so this led to the understanding that this thing must be very elongated, whether it's 10 to 1 or 6 to 1, depending on the phase angle, it's very elongated. It also had a complex rotation state. In terms of chemistry, we can't get much. There was no dust detected at all. And these images show a stack of all the very large telescope 8-meter data, along with various filtering techniques. Just nothing was seen. And this is a model of what 2 kilograms or 200 kilograms of dust would look like. And the same filtering techniques should have showed something. No dust, and nobody detected any gas. However, the gas measurements, there wasn't a lot of time when it was bright enough to do these things. So in fact, the shape has been one of the enduring mysteries, and I don't have time to talk through this whole slide, but there have been a lot of very interesting interdisciplinary papers trying to understand how something can be this elongated, because in the process of building planets, you have collisions, and that should fragment things, or ejecting from a solar system you would think could cause fragmentation. Another part to the experiment that is of great interest for interstellar objects is where did it come from? And the whole point of all the Hubble Space Telescope observations was to try and get sufficiently accurate astrometry to trace the path backwards. In fact, that first effort led by Marco Michelli, Davide Farnacoce at JPL showed that gravity only doesn't work. Very correlated residuals. However, once you introduce an acceleration that varies as 1 over r squared, the residuals go away. So this thing was accelerating. The level of acceleration was completely consistent with what we normally see with comets, cometary outgassing. Yet, no gas was detected. However, from the acceleration, you can model how much water there should have been, or CO or CO2, and there were upper limits on CN that were placed from the observations earlier. And from that, people inferred that this had a bit of an unusual possible ratio of water to CN, which placed it distinctly different from solar system comets, maybe a hint of a different chemistry. But what about the main idea here, which was to try and trace its path back homeward? Well, the Gaia 2 data release had just come out, so it was possible to try the experiment, because you can't just trace the path of the interstellar object. You have to know the motion of all the stars backwards in time that they're passing. And so the task was to find, did it pass within an Oort cloud radius or a few of any nearby stars at a velocity of less than about 10 kilometers per second that it could have been ejected from the home system? And the answer was no home candidates were found. And in fact, I think this may be something that will be actually impossible to do in the future, because when you look at the trajectories of things from the Gaia data release, it's a very complicated problem. And unless you get extremely lucky and it was recently released from something very nearby, it's unlikely that we'll ever trace the home system of one of these things. Second ISO, 2 years later, discovered by an amateur, much better circumstances. It was on its way in, and there was actually about a 2-year period in which it could be observed. and right off the bat, it had a little tail. So it looks completely different from the first one, but just like the first one, Oumuamua, it was red, it was small. However, gas was immediately detected, the first thing you normally see in a comet, CN, not because it's so abundant, but because it fluoresces very strongly. And in fact, many, many interesting papers on the chemistry, but it too looks a little bit different from solar system comets in the fact that this one had a huge carbon monoxide production rate that was seen through direct detection, but also through modeling. Again, the same sort of modeling. If this were the nucleus of the second interstellar object, this is a water model. The very first data looked like you could fit it, but then when colleagues started to find data in the Zwicky transient faculty facility data back in time, and it was really bright, that can't be water. It had to be something more volatile, CO or CO2, and it was probably CO. So the legacy from the only two objects that we've seen and characterized, small, red, they're consistent with comets, but of a slightly different chemistry than our solar system. I think it's unlikely we'll ever be able to track back to their home system. But it's possible that some of these things could have been captured in our young Oort cloud. And so it might be possible through the chemistry of long period comets or short period comets that we'll see something that's so anomalous that it might match what we think is something that's outside the solar system. But I think doing this to really tell the detailed chemistry of an interstellar object may require an in situ mission. So for just the last few minutes, let me switch briefly to NEOs, bearing in mind I'm not an NEO specialist. I did ask Benji what he wanted me to talk about for NEOs, and he said, well, it's mostly from the mitigation point of view, impact hazard. And I said, well, let me put a little science in there. What we've seen more recently from the cosmochemists in 2017, looking at some meteorite classes where we found that two groups of primitive meteorites must have existed in the solar system at the same time. They had the same age, yet they had very different isotopic abundances. The team led by Croyer et al. Suggested that perhaps Jupiter formed very early in the disk around 3 AU, opened up a gap, and prevented the tiny planetesimals from naturally migrating inwards. So you kept two populations isolated for 3 to 4 million years in the early solar system. And the way in which you can get some of this material that we see today in the asteroid belt is it got scattered inwards. And in fact, data from Ryugu, which is an NEO, actually shows that it is very much like carbonaceous chondrites, outer solar system material, which exhibited very low temperature aqueous alteration early in its history, but has been kept cold ever since. Now, from the defense perspective, what you really want to know is the mass of the object and its porosity, whether it's a rubble pile, because this impacts how you will mitigate something if it's going to come towards the Earth. What we've seen from the NEOs that have been visited is that they are likely rubble piles with very high porosity, low density, some internal strength, but very minimal. And interestingly, they seem to lack some fine dust on the surface. So here's some nice images of the NEOs that have been visited from Itokawa, Ryugu, Bennu, and then more recently, Dimorphos with the DART mission, showing their low densities, although this one is assumed to be the same as Didymos. And you can see their spectral class, rocky inner solar system material for these two, and then more outer solar system material here. One of the suggestions for the lack of fine dust on these is that when you have a lower density material, this very fragile C-type material, when it gets impacted, it may just cause compression instead of fracture. And this may actually help explain why fine dust wasn't seen on Oumuamua. And I thought I just had to show some beautiful images from the DART impact. These two images here were acquired from the Aussie Lycia Cube satellite. And Looking just before closest approach, you can see the impact. Here's one shortly afterwards from ground-based. And interestingly, from early October, from HST, it still has a tail, which some speculate maybe there was ice inside of this also, and it's now behaving like a comet. So just a last couple of slides here. You know, we've had a lot of interesting discoveries, especially made by these large surveys like Pan-STARRS. For decades, we discovered the long period comets only when they were fairly close to the sun. You don't get a lot of lead time to study them. When the big surveys started to come online, you see more discoveries, and you see more discoveries at very large distances, so that you do have time scales for characterizing them over years, perhaps. The Rubin telescope coming online in Chile, 8.4 meter telescope. The engineering first light should be, I don't know if it's happened yet, but it's between Q3 and Q4 this year. The system first light will be in about this time next year, and the survey is scheduled to begin in 2024. Now, this is an 8.4 meter telescope. In a single 15-second visit, they're predicting they'll get down to about magnitude 24. And for reference, for something 1 AU from the Earth and the Sun, this would be a 50-meter object if it were really dark, or a 25-meter object if it was brighter. So I think we're going to start to see a lot of things, and bigger things farther from the sun, giving us more lead time. So let me finish with the key questions, the things I think we really want to know to answer some of the science. If you'll notice, the ISOs and LPCs, it's exactly the same. The chemistry, and we want to know about the nucleus. We'd like to know about the trajectory of ISOs. We may get lucky, but I think this is unlikely. We'll trace it back to the home. For the NEOs, it's more or less the same thing, but we really want to get at the mass, the speed, the density, porosity, internal structure from the mitigation point of view. But I maintain you also want to know the same science chemically for what it tells us about the early solar system. Thank you.